was 19 students, was it not? Yeah, I think the problem is this lecture room. Seriously, this lecture room sucks big time because the other room here is very weak. I think it is just that you need to. No, maybe we can. Let me see. Can you see if there's the other room in your phone? No other room. It's gonna take like few seconds when it comes back, and as soon as it comes back, then you can enter your answer. Okay, so maybe what I will do, well, I will do such that I will move on, and I will get back to this Socrative in a second. Okay, then I want to explain to you something that is kind of related to this, or it is related to these eigenvectors, because the eigenvectors are, you know, as they I need to show the answers because otherwise, this makes no sense because I'm about to say the correct answer that is Socrative. So let me see. So you're the only one that is still you on? So it's okay. Good, great. So you go all done. So now the success rate is how much? 100. Okay, pretty close. So what is it now? 95. And if you round it up, what's that? 100. So we close. Okay, the absolute displacement. Okay, don't do anything. Do nothing. Do nothing here. Okay, the absolute displacement for sure is not the absolute displacement because it shows the way. And the absolute displacement would be, the information we need is what? Forces. We need to know forces, and we don't have the forces. We just have the way that the structure performs. Only the way, nothing else. Okay, but what I would like to explain is this. Hold on, so I'm here. So okay, now as the eigenvector is just the way it can deform, I can multiply the eigenvector by any number I want, and still it fulfills the original equation. And my original equation that it fulfills is, I think that I need to go a little bit back. We are aiming to make the mass matrix such the way that the mass after this multiplication will be identity matrix, meaning that the numerical values other than zeros, which are located in a diagonal location, are equal to 1. And this is what is very helpful in terms of the computer implementation, or not necessarily implementation, but the computer simulation. So how can I make it happen? Well, I can make it happen in such a way that I can take the eigenvectors one at a time, and I can put them in this equation and set this equation to be equal to 1. What it means? So it means that I will take my first eigenvector. Well, this is not the first, but the second ID number was 2 because the first one was associated to rigid body mode. So this is my second eigenvector, which I multiply by unknown number alpha 2. Then I have my original mass matrix, and then that again is multiplied by eigenvector ID number 2, and that 2 finally is multiplied by unknown alpha 2. And now this is equation, one unknown. So I can solve the scaling factor. And once solving the equation, my scaling factor will be square root 1 over 5. That's it. Okay, what it means. So I can multiply my original eigenvector by this number to make sure that once I compute my mass matrix, it will be diagonal, identity matrix. Okay, the same way I can compute my scaling factor associated to eigenvector ID4. So here I have my eigenvector, my unknown multiplication factor, my system stiffness matrix, my eigenvector, and my unknown, and I set this equal to 1. I will get the value that is equal to 1. So no scaling needed here. So finally, when I'm using my scaling factor and my original shape, my eigenvector, this is how the eigenvector look like. So these are just the scale by number, and I can scale it any number I want. I can multiply them by 100 or minus 100 or whatever, because this is just the way the structure behaves. And it's not going to change by scaling it. It's just, if I originally have this mode that is shown like this, it would be same to show the same deformation mode by less scaling like this, or more scaling like this. Still is only the way that the nodes are moving with respect to each other, nothing else. You got it? Good. So this is called mass orthogonality or mass orthonormalization, and it is quite often used. Now, when you actually when you have these ways of deformation, and you multiply these ways of deformation with your structural mass matrix, the result is 2 by 2 matrix. This is identity matrix. Like you say, the coupling between the modal degrees of freedom disappears. So there's only diagonal representation. Here, the same, the stiffness, when I do the scaling, this is diagonal representation. And if you look at this carefully, these are the eigenvalues that I computed. But again, diagonal representation. Okay, so here's an example. So example is that I have Fourier vector that is shown here is applying to the structure that we looked at in this previous example. So the Fourier is simply extracting it in one direction. I wanted to solve the response by using only the 2 deformation modes. And the 2 deformation modes that I want to use are associated eigenvectors ID2 and ID4. That's it. So how is my equation of motion? So this is how it looks. So I'm going to take my reduced scaled mass matrix associated to modal degrees of freedom. So it's going to be identity matrix multiplied by unknowns. My unknowns are now these P1 and P2. My stiffness matrix, again my P1, P2. And here's my Fourier that I'm expressing using modal coordinates. And the conversion will happen with help of this mode matrix. Make sense? Okay, so this is finally how my equation of motion look like. And now the beauty of all this is that I can take the modal degrees of freedom 1 and solve that without knowing anything about other modal degrees of freedom. Because if you solve this matrix multiplied by vector, this is going to be shown here. So this is 1 degrees of freedom vibration problem that you can solve without knowing anything about other modal coordinates. This is beautiful story. This is beautiful story. Think about where we left. So we left from the original very large finite element model. Then we conduct the eigenvalue analysis, and we notice that some of the eigenvalues and eigenvectors are not needed, so we take them off. And when we took them off and used the eigenvectors, we reduced the coupling. So the coupling disappeared, and now we have just the 1 degrees of freedom systems, many of them. And by superimposing these results, we will get accurate responses. Unbelievable. Okay, so let's take a look. Is there something else? Yeah, the final responses in terms of nodal degrees of freedom. You can get it by once you're solving the P1 and P2, then you can convert it back to physical nodal degrees of freedom. How you can make it happen? Again, with help of the shape matrix. So you have these shapes, these ways that the system can deform. You multiply that by this amplification, and you go back to nodal degrees of freedom. Makes sense. Group hug? No. So you don't feel this big emotion we're having, we're dealing here. No? Yeah, this is what Jussi is explaining all and over again, isn't he not? Yeah, massing dynamics. This is very fundamental in the model degrees of freedom. That's what they're doing in a massing dynamics all the time. Why? Because this is associated to vibrations. That's why. Here we're using that in a little bit of different reasons or different perspective, but that's it. But again, to make sure that you understand the full picture, what is an eigenvalue? When eigenvalue is the point when you have here the frequency, and this is a response, when the response theoretically goes to infinity. So that's what this is, the resonance frequency. That's what the eigenvalue stands for. It tells that if I, so where's the stick here? So if I introduce the vibration or introduce the force is exactly same frequency that the natural frequency of this stick, the response will get higher and higher, and in theory they will go to infinity. In reality they don't, because of the damping and because the structure, behavior, the characteristics will change if the response becomes really, really large. But in theory, that's what it is. So that's what the eigenvalue is standing for. So it's a natural frequency. So just to make sure that we are on the same page, so this is what it means in practice. Okay, so let's take a look at this. Why not? Oh, yeah, yeah. So I need to go here. You're right about that. Yes. And I need to, I think hold on, one more setting. Yeah, I want to play this. Hmm. Okay, let's see how it is now. Again, I need to be here. Where is it? Nothing. Maybe I need to use this. Okay, no sound. Okay, so I need to be the one that is explaining this, what happens. So hold on. So let me back up. So let me go here. Uh, okay, so I have the system that is a 1 degrees of freedom system. A 1 degrees of freedom system will have one eigenvalue, one eigenvector. And it means that it only have one way it can vibrate, only one way. And the only one way that it can vibrate is showing in this picture. Now I'm adding additional mass. It's like adding additional node. It's the same than that. So now you will have two eigenvalues, two different ways that it can perform, two different deformation ways. So this is the first one, and the second one will be shown a little later. This is the second one. So now what if I'm going to add third mass of this picture? There's going to be three different eigenvalues, three different ways that the system can deform. And that's what's going to happen next. So let's take a look. So here's the system with the 3 degrees of freedom. Again, this is equivalent than nodal locations. So if you have three nodal locations, 3 degrees of freedom, you will have three eigenvalues, three eigenvectors. And these eigenvectors are orthogonal with respect to each other. So they are not the product of each other, but they are independent. Okay, so this is the second way that it can move. And then the third way will be shown momentarily. And let me see. This is the third way. Is there going to be four masses? I guess that there's four masses and that's it. Oh yeah, four masses. So how many different ways it can vibrate? Four different ways. Four different ways. So this is the first. Then there is going to be soon a second, third, and fourth. That's it. Now, in terms of overall performance, if this is a part of multi-body system, the interesting and important question for us is which one of these deformation modes are important? Because this is what we need to look at, because we can eliminate some of the decrease of freedom. And that's what is needed in order to do this modal reduction. So this was the second, third, and then finally the fourth. Okay, so that's the last one. So now let's look at the few examples that are that I'm okay. So here's a few structures that are associated to, these are the real models where we are comparing the deformation modes. And we also comparing the natural frequency, which is the eigenvector, eigenvalue associated to these deformations. Now, what is important here is to take a look at this part of the window, which says some of the modes are enabled, meaning that they are part of the simulation, some of them are disabled, meaning that we are ignoring them. So we are not caring, like if we are ignoring their contribution to final response. I will get started from this one, which is an example of hydraulic uh, cylinder, or more accurately, cylinder rod. And this is a good example because this was a project where the company was suffering the problem associated to hydraulic cylinder. There is a sealing that prevents oil comes off from the hydraulic cylinder in this part of the structure. And this sealing was broken, very frequently. And they expect that the problem is associated to transverse vibration, because the idea of this structure was moving the big load up in the air and then push it down in the ground. So this is a part of the pilot. And they thought, or they assumed, that when you hit this back in the ground, there's a kind of like a shock, like really violent occasion that introduced the vibration in all possible directions. Of course, in axial direction, but more importantly, in this case, in transverse direction. And they expect that this vibration in a transverse direction, that's the one that is killing the ceiling. And they wanted to verify if that's the case by using a simulation model. And then now this model is made by using sets that the cylinder rod is a deformable body, and it is particularly made in order to see like how is a transverse deformation close to the ceiling. So let's look at what are the modes that was involved in a simulation. What were the modes that were disabled? So these are the first ones that are disabled. These are rigid body modes. They look a little bit funny, but they are rigid body modes. So we don't need to use them. So we don't want to use them. But this is a first bending mode enabled. So it was a part of the picture. The second bending mode, part of the picture. Now look at the frequency, is a 90 hertz, so it's quite low frequency. This is 172 hertz. Each one of these modes were included. And then you go higher and higher frequencies. And soon, when you model this based on your solid elements, they look at like this. And this was disabled because we don't know what kind of force can introduce the deformation like this. It's very difficult to do that. This is enabled, disabled. Look at the frequency. That's already more than 1,000 hertz. But still, some of the modes are involved. This is no longer involved. And I believe that the reason is that this is already so high frequency that we believe that this makes no influence to final responses. This is if you model this by using a solid element, there will be tens of thousands degrees of freedom. But we're only using here 20 or less than a 20 in order to analyze the behavior. So we're coming down from tens of thousands to less than a 20. So model reduction is very significant. Okay, so let me do the following. Oh, I did not notice that the time is already this much.